Hello, yeah, okay, just want to check if this mic's working. So thanks for coming, and I'm Ian Harris. Before we start, I just want to acknowledge my students. So if you look at the author list of the paper of this work, there's 8 authors, and the first 6 are all visiting students of mine, so I just want to acknowledge they're not here talking, but they're back home in Korea right now, but I'm very thankful for the coding they did.
Okay, so this is Ian. He is a professor at University of California in Irvine, and he works with hardware verification and security, and of course, natural language processing.
And I'll introduce Marcel Carlson. He's principal consultant at LootCore. He does red teaming, consulting, and security research, and he does a lot of hardware hacking and social engineering himself when he's doing pen testing and that type of thing.
Okay. So we're gonna just rip through pretty quickly to give you guys a sort of context, general stuff about social engineering. Don't worry, it's gonna be fast so we can dig into the cool stuff. So social engineering, right? What is it? Well, there's a pretty good definition by the guys at Social Engineer that it's any act that may influence a person to take an action that's in their best or maybe not their best interest. Because remember, not all social engineering is bad, right? A doctor could social engineer you to do something that's in your best interest, while you may not sort of realize that, right? And remember, social engineering is not a new thing. It's been around for ages. You've had con artists, con women practicing their trade for a long time, decades, centuries. And of course, kids, you know, your kids, they're great social engineers. They will make sure they get what they want, like ice cream. And SE, of course, is a complex concept. There's a lot of sort of components to it. For instance, we have body language, micro-expressions, framing, pretexting, elicitation, and all these sort of things. We don't have time to go into these sort of things. If you're interested in that, you can come see us afterwards if you want to talk about these sort of things. Going into sort of targets, right? So what are targets for social engineers? Well, organization, businesses that are exposed, because remember, it's a typical modern organization will be an ecosystem of technology, people, processes, humans. So there's a lot of juicy sort of trust relationships to exploit for social engineering. And one of the major issues is, of course, that there's, I would say, a big underestimation of the social engineering threat in general. Most companies and organizations have quite low social engineering awareness, and a lot of the business processes and technology implemented, there's usually a burden on the individual user, right, to make decisions regarding security. So it's up to the user whether or not they should click on a link or share information, and that's, of course, awesome for a social engineer, because that gives them a large attack surface to target, exploit, and attack. And talking about trust relationships, again, modern companies, they will have a lot of service providers, business partners, facility management is often outsourced to other companies. So again, there's going to be a lot of trust relationships to target and exploit for social engineers. And how do we do this? Well, of course, you will use open source intelligence gathering to profile companies and their employees. So, of course, you have all the social media platforms that you can harvest information from. And we will automate this using all kinds of tools, scripts, whatever we need to make it effective and scale it up. And there's very good resources such as password dumps, leaks from previous sort of breaches that we can harvest to get user name formats and credentials and stuff like that, and then we have all the sort of technology infrastructure metadata we can gather, like IP addresses, domain names, all the sort of good stuff. I just wanted to show this one because it's pretty cool how it's moving fast in the world of the sort of things we were talking about. Microsoft has recently released a tool called Video Indexer, right? So you can upload a video. Here you can see that fake Obama video from a couple of months ago from BuzzFeed, and you upload that and it will actually analyze that, so you can see who was in the video. We'll do facial recognition, map it against the timeline. It will extract keywords. It will actually transcript what's in the video, so you can get the transcript. And they can even translate that transcript to different languages, and we'll do OCR, so you can get some very juicy metadata from video files quickly now. And it's free, so you can sign up and start using that. Going into the sort of high-level SE methodology, right, to actually compromise someone or a business. It's all about getting trust initially, and then you'll go into a sort of iterative process where you will extract information, influence the targets, keep going. Eventually, you'll have a punchline that we'll talk about, and you will have your compromise, reach your objective. And then we have blended SE attacks, right? You can do it remote to local. And when you do remote, you will typically leverage your social engineering attacks with the various technologies that are available these days, like email, messaging, SMS, voice, etc. And sometimes you need to go there in person and do it, or you can sort of combine these things. Path of least resistance, attackers are lazy, they want to work effectively, and they will just use what works, and that's easy. So most social engineering these days, you don't have to use sophisticated 0 days and stuff like that. You can do basic attacks. Here's an example from the DNC hack, the Podesta guy that got phished. And here's typical, if you guys do pen testing, the sort of things that you will be working with and be familiar with. Here's an email with some, they use some basic obfuscation to bypass the filtering. And there's also some filtering, like a URL shortener to obfuscate the URL to the page where you go and phish them. And you can see there, the URL, it's really lame stuff, but this works. People don't look too closely. You can see here, it's a TK domain, right? They put some subdomains in front of it to make it look like a Google page. There's no encryption, and they used the real sort of picture of the victim from his Google Plus page to make it a bit more believable. And yeah, not very sophisticated, but this stuff works. Talking about what's coming, there's deep fakes out there, kind of an interesting concept. So again, of course, you have porn driving the innovation. So there's sites out there where people spend time to take a porn video, and then they will actually train a tool to put some victim's face on the porn video, right? And that's kind of interesting from a social engineering point of view, because of course you could do that to, again, target trust relationships and maybe spoof someone else's face on a video, like the Obama video. And another interesting concept, adversarial games. It's all about sort of a cat and mouse game between someone who's producing fake content, and then you submit that to someone who will review it, and it goes back and forth, and the faker, so to speak, will become better at producing fakes, and the part or the sort of party who will review it will become better at spotting the fakes. And if you take this into the sort of machine learning, cognitive science domain, there's some really cool stuff being worked on right now, like generative adversarial networks, GANs. It's the same concept. You'll have a generator training on samples, submitting the fake samples to the discriminator that will compare the fake samples with real samples, and the sort of data that comes out of the comparison will be back propagated to both the discriminator and the generator, so they will both become better. And again, taking this back to social engineering, this could be used to train a generator to produce or generate a fake sort of audio sample, for instance, to spoof someone's voice, right? So that'd be pretty cool if you need to attack an organization. So it's pretty much doom and gloom. Businesses are exposed and social engineering works. So what do we have? What can we do to protect ourselves? And this is where this research comes in. So I'll let Ian kick it off.
Thanks, Marcel. So just to sort of say what the tool is that we're presenting, what it does is, it's this yellow box here, okay, right there. Social engineering detection. So what it does is it takes text which is spoken to you by an attacker, let's say, or maybe emailed to you or something like that. It analyzes it sentence by sentence to see if it's something suspicious. And if it's suspicious, it looks like it's an attack, then it'll warn you in text. And if it's not suspicious, then it lets it go. So that's basically what the tool does. And so you could use it with a texting application or an email client, and that'd be trivial because it's already in text form. Or you could use it if you had sort of an audio video device like a phone, right? You'd have to have a speech to text engine on the front end there, right? But you could do speech to text in real time and then feed that to our tool too. But our tool, as it is now, it takes text. Also, one thing I'm just noticing, people are taking pictures of slides, which is cool, but this version of the slides, I'm going to put on the GitLab site. So at the last slide, maybe take a picture of that. And all the code is up there at the site, and also I'm going to put these slides up there, which we just sort of modified right before we walked in. So you can get a copy of all these, no problem. All right, so yeah, so the way we detect these social engineering attacks, they're pretty complicated. Like Marcel was saying, there are a lot of sophisticated ways somebody can fool you and get you to do whatever they want you to do. But in the end, we claim that the attacker has to do one of two things. Either they ask some inappropriate question, some question whose answer is private, like what's your password or something like that, or they tell you to do something. They give you a command. They tell you to do something you shouldn't do, like click on the link. Okay? So it's either a question, an inappropriate question, or an inappropriate command. And so that's what we're looking for. So we're not detecting any of the attack before that, right? They might be conning you and saying they are somebody who they aren't or something like that. We skip all that and we wait for this, right? We're calling this the punchline, right? At the end, they're going to have to do this ask, and that's what we're trying to detect. So there's a demo at the end of the talk, but in case the demo is a big fail, I thought, okay, let me put a little video in here just so you can see what it'll do. So this is it. Let me start it, and I'll just talk through it. So yeah, okay, there it goes. Get that out the way. All right, so I'm about to start it. I think my students called it temp, so I'll start running it in just a second. There we go. So run the code, and basically it gives me a prompt, and I have to enter a sentence. So I think I start off with just some random sentence that, have a nice day or some nice weather we're having. It doesn't matter, right? So that shouldn't flag anything. So you hit enter. The first one takes a while. Yeah, there it goes. Normal sentence, it says, right? And I'll highlight it. Yeah, normal sentence. So now I'll put in something malicious, some command that's malicious. So I'll type, give me money. Okay, that's suspicious, right? So suspicious. So scam detected, right? Scam detected, and it found the direct object pair, give and money, right? The verb and the direct object, and it looked that up and said that is suspicious. Now, we're not just looking for give and money, though. We're not just looking for words. We're looking for how they're using a sentence. So here I'm typing, give me a poodle for money, right? Now, it's a stupid sentence, but it's not malicious, and it has the same words. It has give and it has money. But this one, when I hit enter, it will not detect. Yeah, there it goes. Normal sentence, right? And notice that it finds a verb and direct object pair. It says it's give and poodle is a direct object this time. Money's in the sentence, but it is not the direct object. So it realizes, okay, this is not malicious. So that's, now I'm asking a question. I forgot. What is your password? So I can also ask questions. What is your password? And it's going to say, it's a question. And it's going to tell me it's bad. Yeah, there it goes. It says scam detected, right? So it basically said, okay, password, if you ask about password, that's malicious. I'll tell you how we do that. And then I think I ask an innocent question too, and it doesn't flag anything. What is your age, okay? And that's not considered malicious, and so fine, it's a normal sentence. So that's basically, I'll do a longer version of that at the end, assuming I'll get to it for sure. But anyway, that's how it will work, assuming it works. But that's how it does work. I recorded this last week. All right, so this is the structure of the system. And I'm not going to talk about all of this. So it starts off, though, with text. Text in some form. We use a bunch of phishing emails to evaluate the system, but it could be any text. And in the end, it produces malicious, or it filters it out and finds malicious sentences in the text. And basically, the way we do this with emails is, if any of the sentences in the email is malicious, then you say it's phishing. But you can do this verbally, too. Any sentence you say, if it's malicious, then you'd give them a warning, okay? So there's a bunch, the main things I want to focus on are over here. Sentence processing is just putting in punctuation in case somebody didn't. But you get sentences, you got to identify it. Is it a command or a question, okay? And maybe it's neither. If it's neither, we ignore it. If it's a command, then we got to do command analysis to see if it's a malicious command. And if it's a question, then we got to do question analysis to see if it's a malicious question. So I'm going to really talk about figuring out if it's a command or a question, and then how we do question analysis and then command analysis. Actually, Marcel will talk about that part. All right, so detecting questions and commands. So we got to be able to take these sentences and figure out if they are questions or commands. So the basis for that, and actually most of the stuff we do, we have to parse the sentence, grammatically parse the sentence. So we use a parser, an off-the-shelf parser, Stanford parser, and there's a site where you can get it. Stanford parser is sort of a well-used parser. Everybody uses it. And what a parser does in this case, this type of parser, it generates what's called a parse tree of the sentence. It finds the parts of speech of each word, and then it groups the words into grammatical structures: noun phrase, verb phrase, different types of clauses, all that. So you get a tree in the end that shows you the structure, the syntactic structure of the sentence. And a lot of our analysis depends on the syntactic structure of the sentence. We analyze that structure and look for patterns, basically. So here's an example of how we might detect a question. So it's like yes/no questions, right? One way to make a yes/no question, like here's a question: can I eat? Now, compare that to I can eat. The way you make I can eat into a question is you take the I and the can and swap them, right? You invert the modal and the subject. So now here's the parse tree, and VB is for verb, this is for a pronoun, this is for modal, and so on. But we can look at this and recognize that this is a question. Actually, in this case, this type of question, you had to invert the subject with the modal verb, and that SINV tag, that's what that means. That stands for subject invert, right? So basically, if we look at the parse tree, we see an SINV tag in there, we know it's a yes/no question. Also, SQ tags serve a similar function. And there are other types of questions too. I'm not going to go through them all, but there's a white paper that I think you all got, and it goes into more detail. There are open-ended questions. What is this? Where is this? And there are different tags that we can identify inside the parse tree that tell us if it's a different type of question. So that's how we. So basically, we look for patterns inside this parse tree to determine if it's a question. Now, then we also have to detect if a sentence is a command. So there are different types of commands. Probably the most common type is where you have a verb and no subject in front of it. So instead you say go home or stop right there, right? It starts with the verb. And it doesn't say I go home, it just says go home, no subject in front of it, right? Or stop right there. So that's how you detect a command, and we can just look for the verb, see if there's a noun phrase before it. If there isn't, then we say it's a command. There are a few other patterns too. Attackers you don't want to give a direct order like that because it seems rude. You want to say, please go home, or something like this. We can identify that. Also, another way to do it is they sort of suggest to you, like you should go home, you might go home, right? You could go home, something like that. So we can detect that pattern too. It's basically you and then a should and could. I forget the type of word that's called. I'm blanking right now. But there's a particular type of word that word is. But anyway, it's easy. So we have several patterns in addition to the one you see here where we can identify if it's a command. So we do that. First, we figure out if it's a question or a command, and if it's neither, then we just ignore the sentence. Okay, so say once we've done that, we detected questions and commands. So now we got to analyze the questions, analyze the commands. So the command analysis is right here. Command analysis, what we do is so our goal, we're going to say a command is malicious if the answer is private data. Okay, so what we do is, like, where is your bathroom? The answer is not private. What is your social security number? The answer is private. So how do we do that? So what we do is we use previous research in question answering systems. Now there's a lot of research going on in question answering systems, and the idea of that is you write a question in English or in a natural language, and it finds the answer for you, either in a massive database of facts or over the internet itself. Lots of companies try to do this directly from natural language. And there are tools out there, and we basically found one open source and just started using it and modified it a little bit, okay? Now, they don't work too well, okay, because it's a hard problem. So like the tool we use, it gives you the correct answer 44% of the time, which is low. But with our modifications, and since we don't actually need the answer, we don't care about the answer. We just want to know, is it private or not, right? Given that, we can get it to work well for us like 99% of the time to determine if it's private or not. Even though we don't provide the answer, we still can tell if it's private or not. So I'll explain that. Okay, so the structure of the question answering system, the type we're using is looking through a structured database for the answer. So the idea is you got a question in English, the tool generates a bunch of queries, like this is a SQL query, right? And then it just looks it up in a SQL database in the table and it finds the answer. It finds it or it doesn't. That's basically how the tool works. And the tough part is taking the English and making the query, right? Once you got the query, looking it up in the database is fairly straightforward. So what do? One modification that we do, we basically, instead of having a database full of millions of facts, we only have a database with the private information. So the information we consider to be private, the facts we consider to be private, we put information about that inside the database. Then, if it finds an answer, then you know it's private. But if it doesn't find an answer, then it's public. Okay, so we have a much smaller database. There might be 15 million facts in a real database. We got like 100, the private ones, right? And we, right now I'm showing a label here. It's a private label. Also, I should note, we don't keep the actual data. We just keep if I thought President Obama's age was private, I would keep President Obama in there and a relation. I'll show it to you in a few slides. But I wouldn't keep the actual answer in there because I don't want to have a database full of private information because if somebody stole that, that'd be all over. So, but we don't need the information in there. We just need to know if we can find find the entry in the table, then we know it's private. Okay, so the system we use is called Parallax. Here's their paper, and you can look that up. And this is a subset of their database. So their database is one massive table of over 15 million entries they culled off of Wikipedia. And there's a relation and two arguments. So official language of Hong Kong is Cantonese. Plural for bacteria is bacterium, and so on. And it's just a pile, like millions of these triples that they have, and they search for answers in there. So we use that. We didn't make that. We just use that. And they take natural language question, they make the query from the natural language question, and then they look it up and get the answer. Okay. Now, one thing, like I said, the question answering tools don't work too well. Okay. So what they do is they don't make one query out of a question. They make like 30 queries, 30 possible queries, because they're guessing at what the query should look like. And that's sort of a long story how that works, but they make a lot of guesses. So they make like 30 queries, and then they rank them according to a metric. And then they pick the top ranked one, and that's the one they use to look up the database. So this is an example of that where, actually this is an example of their tool. You ask this question, here are two queries that they find. The top ranked one actually gives you the wrong answer. The second ranked one gives you the right answer, okay? And so the reason why they get low correct answer rate is because, somewhere in their top set of queries, they're gonna have the right query, but if it's not the top one, then they give you the wrong answer. Okay, so we loosen that restriction ourselves. So one thing we do, first thing we do is we only contain the private data in the database, which you would personalize that to your assets, right? So whatever you wanted to protect, you put that data in the information about that data in the database. Then what we do is we look at the top 15 queries. Rather than looking at the top one, we look at the top 15 queries. Now what that does is it increases the rate of true positives, right? Because if it's not the top one, maybe it's top 2 or 3. But it can also increase the number of false positives because maybe something really isn't private, but query number 15 or 14 is something that's private, right? Maybe. But that is an extremely rare occurrence because if you take 15 random pieces of data out of like the original database of 15 million facts, it is very rare that those random 15 are going to be coincidentally in this private subset. Okay, so the number of false positives, the increase in false positives is really small doing it this way. So that's what we do. So that's how we analyze the questions, and we determine if they're private or not. And now to talk about the command analysis, Marcel's going to continue. I don't know if you want this.
Okay. So we've looked at the question, and now we're going to look at the command. So the command analysis is all about to find out whether or not it's a bad command or not, right? So you can see the example here, take a left at the next corner. That's not very sort of interesting. Whereas if someone asks for your social security number, that's bad stuff. That's something we need to flag as bad and so if we look at how we sort of represent a command, right? So what we do is we apply the verb direct object sort of concept. So again, you can look at the first example, take a left at the next corner. So that will be represented by verb and a direct object, take and left. And then we have the bad example, or the sort of attack. Please give me your password. So give and password. So you can see it's quite a nice concept to make it easy to deal with, because what we would do is to create a blacklist, right, of the stuff that we need to flag on. So we, again, as for some of the previous stuff, we used a existing sort of solution that we tailored for our little research here. So in this case, it's a Stanford type dependency parser we used. And this tool or solution allows us to determine the relationship between words, right? So you can see there's something called a DOBJ. And in the sentence, please give me your password, it will actually sort of identify give as the verb and password as the object, right? And you can see that number 2 and 5 represent where in the sentence these sort of objects occur. So we would like to then create a blacklist that we will use to trigger the bad stuff that we need to sort of flag, right? So we looked at a bunch of phishing emails. There's these sort of Enron emails that we looked at. There's about, what is it, 180?
The Enrons are the non-phishing ones.
Okay.
And then we had a bunch of phishing email sources.
Exactly. And then we actually applied this sort of metric called TF-IDF. You might have heard that because it's used a lot in this type of sort of research. It's term frequency inverse document frequency. So that's the metric we applied. So then we looked at in the phishing emails, we saw what was ranked as high, right, these sort of pairs, and then we compared to what was in the sort of non-phishing emails, right? And then we could compare that and extract the sort of things that a typical phishing email would contain to produce a blacklist. And as Ian mentioned before, remember, we looked at these sort of phishing emails, but of course you can sort of create your own blacklist based on your company, your organization, the important stuff that you may have, crown jewels. So if you take, for instance, an insurance company, it will be different from a hospital, the sort of information that's important to protect, right? And then you can take your crown jewels and look at your risk assessment, what's important, what needs to be prioritized, and then you create your own blacklist to have a custom sort of solution that makes sense for you. And now Ian will do another demo to show a bit more in detail how this sort of stuff works.
Okay, thank you. Yeah, so now walk through the demo. If it works, let's close that up. But you saw the video, so you know it works. Okay, so this is virtual machine. I'm running an Ubuntu instance. There's 3 windows, right? There's the big one in the top middle, right? And the big one on the top, that's where I'm going to type in the questions or type in the sentences that it's going to analyze. The one on the lower left is for parsing. So that Stanford parser is basically a parser. It's a server, the Core NLP server for their parser. And then the bottom right is the question answering tool that we downloaded and installed. That's running in the bottom right. And so it's only going to be active. It's only going to do anything, show anything in that screen when we ask a question, right? And then that question answering tool, it sends data to the parser in the lower left. But anyway, I'll type a sentence in. Okay, so let's type an innocuous sentence. Assuming it works. Hello there. Okay, fine. Normal sentence, and just to highlight it, it says right there, normal sentence, whatever. Okay, let's try some command. Give me money. Scam detected, yeah. Okay, so we saw that, yeah, that still works. And it found the verb direct object, give, and money. And it looked it up in the little table in the blacklist, and that was that. Now, if I said, give me a car, that should be fine. Yeah, because it found give and car, so it says normal sentence, found give and car, and there's no harm there. But let's say this is a car dealership and you want to make sure people don't give away cars. So you want to put that in there. So you want to put give and car in there as something that's a malicious command. So you would go, so basically it's reading these verb direct object pairs from this blacklist file. And for us, that's, we got a little JSON formatted file. Here it is. Maybe it's a little hard to read from back there, but give money is there, send money, give resume, hope money, whatever. There's a bunch of them. And this is just this is just a little sample one for the demo. We have a much bigger set that we got from the phishing emails when we got our results. But I can add an entry into this without difficulty. So I said I wanted to make it give car be malicious, right? So I'll just add that in there. Give car.
And all the zeros are just options that we're not using. I mean, there's a bunch of sort of advanced features, but for this sort of proof of concept, we're not using them. So that's why Ian's putting a bunch of zeros.
Yeah, or they're letters O. They're actually O's, but
yeah, zeros, O's.
They're to be ignored, put it like that. But I put give car in there. Now let me save it. Okay, it looks like it's saved. All right. Then let me stop this thing and run it again. I got to run it again because it reads the blacklist when it starts. So if I run it. Okay, and now if I say give me a car, it should detect it. Let's see. It slowly analyzes. Got it, yes. Scam detected, give car. So, okay. So those are some commands. Now let me try some questions and do a similar thing. Let's try, what is your password? And that should be detected as a scam. So it detects as a question. Yeah, scam detected. Excellent. Scam detected. And now if I say, what is your age? It should be fine because age isn't in our database as something that's malicious. So normal sentence. So let's say now I want to put the age actually in there. I want to make it so that the age is something that's malicious, something secret. So what I'm going to do is I'm going to go down to this lower right here. So remember when I said that when you ask it a question, it makes a bunch of queries, right? It makes not just one, it makes a whole set of queries. And you know what? Now I've messed up. I can't see it well. Let me ask it again. It's hard for me to find the thing I wanted to scroll to. I'll just ask it the question again. What is your age? Okay, so normal sentence, but you'll notice that on the lower right, it printed a bunch of junk. So what it printed was all the queries that it created, all the SQL queries. And so I'm just going to scroll through those to the first one. If I can find, yeah, there it is. Yeah, this is it. Okay, so the top ranked one was this guy. And it's looking for could be as a relation and then aging as the entity. I don't know how I got those names, but that's the top ranked query. Now, and that's not in the database, right? But I can put that in the database, and then it'll detect it as being something secret. So I can say, look, the age of somebody my age is secret. Let me put it in the database. So let me do that. Let me open up this database. It's already open, but yeah. Here it is. It's tiny, but here's some of the facts we have. Notice there's 3 columns, a relation, arg1, arg2, and one argument is always marks the thing that we're trying to record. One says confidential, so it's just sort of a dummy. But the other one says, like, for instance, your password. What is your password? So password is the entity there. So I'm going to add another record in there to make sure that that first query actually triggers. So I could say, could be .r, that's a relation. I'll put confidential in here, .e, and aging, all right, .e. Okay, now if I save this guy, write changes. Now, I shouldn't have to rerun it. I should just be able to ask the question and it should read it from the database. So let's try it like that. Sometimes it flakes out, but what is your age? It worked. Yeah, scam detected now. Because I put that fact in the database and now it registers it and it knows it. Somebody asks about what my age is, it'll say that it's a scam. And yeah, that's the demo. So now, let's go back to the talk. Where's that talk? Here it is. Yeah. Okay. So what we did was we wanted to evaluate it. And the best way to evaluate it would have been to use, I should mention this. An important part of this research, an important good thing about this research as compared to other techniques that detect phishing, right? There are other techniques out there that detect phishing. One good thing about this is that it can be applied to non-phishing, meaning these social engineering attacks can be given to you by phishing, or you could do it in person, right? Or you could do it over the phone, right? Phone's very common. So any of these other vectors, the other previous techniques focus on phishing, right? And phishing, you have a lot of metadata available, right? In the email, you got like URLs you can look at and header information you can look at. Like a lot of phishing email detection approaches, what they do is they'll somehow figure out, look, did this email come from who it says it came from, right? They'll use header information, URL information, other stuff like that. But they don't necessarily look at the meaning of the sentences in the way that we do. But since we're looking at the content, the actual sentences, and trying to analyze the meaning, it can work with phishing emails, it can work with in-person text or texting or over the phone, right? So the best way to evaluate this would have been to use other vectors, right? To have phishing, social engineering conversations recorded and feed it in. But those don't exist. And if anybody knows of some that are publicly available, please give them to me and I will try it out. But you can't find that. But you can find phishing emails. So we went to some websites and found a bunch of phishing emails. And so we analyzed it by running on these phishing emails. So altogether, we had about 187,000 phishing emails. 100,000 we actually used for training. And when I say training, it's not machine learning, but when we're trying to find the verb direct object pairs, we analyze 100,000 phishing emails and 100,000 Enron emails, which are non-phishing, to see which verb direct object pairs occurred most frequently. in the phishing emails and not in the Enron emails. And so 100,000 we use for that training in that sense. And so we evaluated on the other 87,000 phishing emails. And then also another 87,000 Enron emails. So, okay. So here's what the results look like. Now, this table over here, this column of the phishing emails, this column is the Enron emails, and this row is how many are detected and how many are not detected. Now, what you want is for all the phishing emails to be detected. So you want this to be, this number in this box to be 87,000, okay? And then you want all the Enron mails to be not detected. So you want this to be 87,000. And then you want these two to be 0 and 0. You don't want any Enron mails to be detected. You don't want any phishing emails to be not detected, okay? That's not what we got, but these are the results, okay? So so this is what we got for precision and recall. The problem with these guys, these false negatives and false positives. So I'm going to talk about why these results aren't as good as they could have been. So let me talk first about the false negatives. So to look at these false negatives, so basically 35% of the phishing emails were not detected as being phishing. So why did that happen? Well, most of the reason why that happened is because our approach only detects this punchline of the attack, okay? So basically the end of the attack, the point where the person does the ask. They say, okay, give me your password, right? Tell me your password and I can help you, something like that. They give you a command or a question that's malicious. All the rest of the email, all the rest of the conversation, we don't analyze that really. We just let it by, right? And the problem is, so like pretexting, elicitation, we're not even trying to detect that. And the problem is a lot of these emails were just pretexting, elicitation and didn't get to the ask, okay? So usually these like say it's a phishing email, and they'll just say, like the most common thing is the email will just say something like, yeah, hit me back, contact me, right? Just that. And then you would get into a conversation with them and eventually in some email, they ask you for money. Right? We would only detect the one at the end where they ask you for the money. All the other ones we miss. And a lot of the emails in these databases, the phishing emails, were just like that, where all they asked you was, to contact me or something. So here's an example of one like that. Actually, the way we looked at this was, I had the students look at 100, randomly selected 100 of the phishing emails that were not detected, and sort of manually figure out why were they phishing and why did we miss them. Okay? And 79% of those, meaning 79 of the 100 mails that we looked at, they were earlier in the sequence in the conversation sequence, and they didn't have that punchline. So for instance, here's one. I put some ... This is sort of standard junk, right? ... And then if you're interested, please you can call us or reply us, right? And that's all they ask you to do, just contact us. And 79% of these emails that we didn't detect, phishing emails we didn't detect, were like that. All they asked you to do was contact. And we didn't call that, we didn't recognize that as being an attack. So because it's not at the punchline yet. So most of these emails we didn't detect, these phishing emails we didn't detect were because of that. False positives on the other side, 16% of the Enron emails were detected as phishing, right? And they weren't phishing, but they were detected as phishing. That's mostly because of this, the blacklist that we make, okay? The verb direct object pairs. So the problem is you got to have these verb direct object pairs that you see in phishing emails, but you don't see in Enron emails or in non-phishing emails. And so 97% of these 100 had innocent commands that we labeled as being malicious. So for instance, pay and a number, okay? Pay some amount. So that, we said that was malicious. And which it sounds suspicious, right? But, in these Enron emails, people were asking you to pay. Like, hey, pay me the money you owe me. I don't know what they were saying, but there were Enron emails where they used that verb direct object pair. So this is sort of so what do we do about that? What can we do about that in the future? One thing is to change the blacklist. Now, that wouldn't help with that particular problem I just mentioned, but there's one thing that would fix a lot of it. See, part of this is that the blacklist creation is noisy. In order to automate the creation of the blacklist the way we did, because we wanted to look through 100,000 phishing emails and find these verb direct object pairs. But we considered any verb direct object pair that was in a phishing email, we considered that to be suspicious when we were counting. But really, if you get a phishing email, maybe it's 10 sentences and 9 of them are innocent and only 1 of them is malicious. But we just considered just to make it easy to automate, we just said, okay, everything is malicious. So you get a lot of noise in there. So you get a lot of these pairs that might not specifically be related to phishing or related to social engineering attacks. Now, part of the way you're going to fix that too is when you make these lists manually, we did it automatically in this case using the TF-IDF metric, but you can and should make this blacklist manually to fit your circumstance, right? Whatever assets you want to protect, whatever operations you don't want people to do, you put that in the blacklist, and then you would get a much cleaner blacklist and get better numbers than what we got. Now, another possibility is that we only use the verb and the direct object in the sentence. We may need more information out of the sentence than that. I mean, we throw away large chunks of the sentence. Maybe we need the indirect object, give money to my mom or something like that. Maybe I want to know the rest of the sentence, right? So the indirect object of the sentence or something like that. Maybe there's a prepositional phrase, it adds something, and we need to use that. We're going to experiment with that basically over the course of the next year. We're going to be experimenting with that. What other information can we pull out of the sentence? Maybe we can get better precision and have actually specifically better recall. Okay, and then different ways to do bypass. Actually, do you want to talk about this?
Go ahead.
Okay, so bypasses. So how might one bypass our approach entirely? So here's 3 ways that we thought of that somebody could do. One thing is don't ask a question or issue a command. So if you can suggest a command or question without saying it, then you would avoid detection with our tool. And I'll show you an example of that next slide. Another thing is you could state your question or command in a way that uses non-traditional grammar, slang or elite speak or some junk like that we can't parse. Then, and you could improve parsers to make them parse more of this. I mean, so these parsers, like a Stanford parser, is pretty good actually. It deals with some slang, but there's a limit to it. Also, you can state the question and command in a way that our system was not trained for. So there's machine learning underneath our tools. So specifically, the Stanford parser, it was developed using machine learning techniques. Also, the question answering tool that we're using, it was developed using machine learning techniques to learn the patterns of questions and what they look like. And if it was trained badly, then all those problems would sort of propagate to our tool too, since we're depending on those tools. So example, first thing, like not asking a question or making a command. You could explicitly say, what is your password? We detect that. Or you could say, I can reset your account, but I'll need the password first. So you didn't exactly say, what is your password, but it's pretty clear what you want, and the person may give up their password. So you didn't say, you just suggested the question, right? Also, command, you can do the same thing, reset the router. Or you could just directly say it and we could catch that. Or you could say, I can fix the problem, but the router needs to be reset and I can't do it from here. So I didn't tell them to reset it, but it's pretty clear I want them to reset it. Things like this, we can't detect. Non-traditional English, so this is like lead speak or slang or something like that. Also homoglyph attack. I don't know if you know about this, but basically using characters that are very similar. So what is this looking at? Actually, Marcel, can you explain this one again?
Yeah, it's the good old trick, right? You can use kind of weird ASCII characters, so use some from other languages. So there were an example with blackhat.com, that's what you try to sort of spoof. And then you can see that we have actually altered 3 letters with some weird sort of alternatives that will have different ASCII characters. And if you look at the bottom there, that's sort of the result using the altered characters. So it still looks kind of like blackhat.com if you look at it in an email, and that's the way to sort of get around filtering, right? So that's another way. There's 100 ways you can do this. Mm-hmm.
Yeah, so that's something that we wouldn't be able to detect. Now, there are other approaches to deal with that. In fact, we saw a talk on that just the other day.
Yeah, exactly.
I like that at B-Sides, actually. But and then incomplete training in general. So like I say, these techniques work on, so we're using machine learning techniques underneath. We didn't do machine learning, but the tools we use have machine learning. And if they were trained badly, then that would propagate to our tool too. Also, the topic blacklist, like I said, it has a lot of noise because of the way we trained it. Actually, manually making a topic blacklist would make more sense and you'd get better results. Future stuff. So one thing we're going to do, one issue with this work is that, I claim that this work, you can apply it to not just phishing, not just email vector, but also in person, any text, in person, over the phone, or through texting apps. But it would be useful to actually try it out against those, right? We only tried it out against phishing emails because that's all we had access to. It would be useful to try it out against other types of other vectors of attack. Now we didn't have any, but we're going to make some. So basically, I just got a grant where I'm to okay, if you know the social engineering village, you know, they got, and DEF CON, they capture the flag, right? We're gonna do that. We're gonna pay students 15 bucks. And I'll tell them, look, in the next 3 months, we are going to attack you and steal some data from you over the phone, right? And I'll tell them this, right? I'll say, look, we're gonna call, I'm gonna pretend to be one of these people. I'm gonna try to steal one of this set of data. Now, I'm telling them, so that will skew the results, but they're gonna forget, guaranteed they're gonna forget. So I'll call them 2 months later. Actually, we're gonna do it vary in times to see how long it takes them to forget. I'll call them, you know, 2 months later, and then I'll attack them, and they're gonna fall for it every time. I can almost guarantee. But we're gonna see, right? Not just me, I have a bunch of students doing it, but we're gonna basically make a bunch of synthetic attacks, and then see how often they work, and then we'll have a set of attacks that we could say, look, this worked 80% of the time, 90% of the time, so this is valid for us to use to evaluate our technique. Then also, eventually we're gonna start looking at, in general, we're gonna look at authentication of the person, okay, the speaker authentication. So knowing who the speaker is important. We don't know who the speaker is, right? We assume that whoever's speaking is unknown to us, right? But really, it would be good to know, like if your mother tells you, says, give me $100, that may be okay, right? But if a stranger does, then you shouldn't do it. So it would be useful to know who is speaking. So we're talking about using audio techniques and stuff like this, and what are these networks again?
Generative adversarial networks.
Thank you. I always forget those initials. But basically, people could train a speech engine to copy another person's voice over a period of time and to spoof somebody else and fool us. And we'll be looking at these things to see if we can do authentication over the phone or some other way. And this is the web page I was talking about, where we have all the code for this, and I'll put this actual talk up there too. It's not up there at the moment because we just changed it, but I'll stick it up there, I don't know, tonight or something. And that's it. Thank you.
Yeah, thank you.
And questions, right? Go ahead. Could somebody turn on that mic? Hold on a second. He'll get the mic on because I can't even really hear you. Does it have a switch maybe? No? You could yell. You could say it to me? Okay.
Okay, how about that?
Yeah.
So I have a question about deliberately false statements in social engineering attacks. So should I just email them to you at marcel@pornhub.com?
Go ahead.
Yeah, go ahead. Fine.
So the question is, though, how would you deal with that, right? That is not a question. That is not a command. That is a deliberately false statement seeking a correction from you as the target, which is often given.
We can't detect that.
Okay.
Yeah, we can't detect it. Look, this is just a start, right?
No, absolutely. I understand. I was just curious if that was something that you guys were planning against or.
Yeah. No, we can't detect that. Yeah. Question?
Yeah. So you've addressed a lot of the kind of false negatives or false positives that you would have gotten. But one question I had was like, if you had like a hairy dog story, like, oh, hey man, I forgot my speaker pass. I really liked your talk. I know there's a party later. I don't know if you're going, blah, blah. Maybe I can tag along. You know, some big long thing. So some long sequence where I can't remember the term you have, the punchline is like spread across.
Oh yeah.
The text.
So at the punchline. So right now we are detecting one sentence punchlines. If the punchline is spread, so for instance, let me give you a little example how you might spread a punchline. You might say, yeah, I need the password. Can you tell me what it is? So you're using a pronoun. Can you tell me what it is?
Yeah,
right?
any co-reference.
And so you're referring back to a previous sentence. We actually don't do that at all right now, but part of that can be done. Like for instance, they call that pronomial anaphora resolution, figuring out what the pronoun's referring to previously, and that's a done thing. People do that in natural language processing. That we could do, but in general, the problem that you're talking about where, you have to, in order to understand this sentence, you got to know the context before it, that in general is a hard problem. I mean, pronouns, it's not so bad, but in general, we can't do it and it's hard.
Sequence length could also be an issue because,
Yeah.
if you're feeding it into a regular LSTM, it's going to forget after a while.
Yeah.
You'll need a model that's robust for whatever kind of arbitrary amount of text that you're going to deal with.
Mm-hmm. Yep.
So, yeah. Thanks.
Yep, sure. Question?
When it came to false positives and false negatives, what occurred to me is, didn't the Enron database have a bunch of phishing emails in it? And was that
Look,
something you
I
had to
don't
prune out?
know. So did the Enron database have a bunch of phishing emails in it?
It
I
must have.
assume not. I don't know for a fact. I mean, I didn't go through them by hand. The database that I used, the emails, the text that I used before, I found like Supreme Court justice records, right? Like Supreme Court transcripts. I said, okay, there can't be phishing in there, right? And I used that, but I wanted, oh, should I stop now? Questions too? Okay, but yeah, so I don't know. I assumed it didn't have phishing email in it. Maybe it did. And then maybe I got much better results than I thought. Yeah, I'm not sure.
Thanks very much.
Yep, sure. I should stop now? Okay, so we got to take it to the wrap-up room, but thanks a lot for coming.
Yeah, thanks.